Welcome Algebra 2 students to our video on the graphs of cosine and tangent. And this is exactly how I feel when I think about doing trig. Very excited and happy. This is one of my favorite memes, and you're going to understand it later on in the video, but this is a tangerine. So be willing to go back and rewind to this spot, and I'll remind you where to do it. Let's start with a brief review of the graph of the plot of sine, the sine function. So remember, this was our basic formula here, which we had a lot of bells and whistles on this because we looked at a vertical stretch or shrink with the amplitude. We looked at a change in the period, which is the time it takes to do one full cycle. That's one above, one below. This would be two full cycles right here. So this had to do with our period for the function, which was 2 pi. C is a phase shift. It has to do with a horizontal shift, and then D was a vertical shift. And we learned that the basic sine function starts at 0, 0. At pi over 2, it goes up to 1, so it curves with a maximum at 1, curves back down, because at pi it's back at 0, goes to -1 at 3 pi over 2, and back to 0 at 2 pi. All right, so that's the basic graph of sine. Cosine is very similar, but starts instead of with 0, 0, it starts with 0 degrees is at +1 for the y value. So start with, let's think about what the basic form of this would be. It is the same as what we looked at before with sine. So y equals a times cosine of the quantity bx plus c, and then we add d at the end. And it's the same thing that we dealt with before. A is still our amplitude. So that number out front is going to change the height of our curve, of our cosine curve. Gosh, it took me a second there. Take 2 pi and divide by b, and you find the length of the period, because the basic period of cosine, like sine, is 2 pi. So it starts here and goes to here, where it ends in a peak to a peak. So peak to peak or trough to trough, that's one period of cosine. It's usually considered peak to peak, like that. And then again, if we take get my writing tool, bx plus c, and we set that equal to 0, that gives us our starting point. Okay, it gives our starting point of our graph. So if I set that equal, that'll give us where the y is 1. So instead of 0, 0 being that starting point, this gives us where y is 1 when we solve this equation. And then d is your vertical shift or vertical translation. If you wanted to look at what exactly your horizontal translation is, it's actually called a phase shift. That would be b divided by c. B divided by, sorry, got that backwards. Fix that. C over b. I don't know why I thought b over c. C over b, and that would give you your phase shift. That's your horizontal shift. Okay, so if again we have a function that is changed in a myriad of different ways, remember that a, that amplitude, that's that distance from the middle line up to the highest or lowest point. So 1 this way, -1 that way. All right, and then 2 pi over b, that gives you the length of the period. So you take this value, 2 pi over that, it gives you how long it's going to take to get from one end to the other. Okay, and then we have the starting point where we start the function. That has to do with that phase shift, that horizontal shift. But if we set this equal to 0, that'll tell me where y is 1. And then the vertical shift would move our midline. So if I moved the midline up or down, it would be because of a vertical shift. Okay, so let's compare them briefly, because there is a very cool relationship here. If I take y equals the sine of x, I can actually just as easily write this. So this would be y equals sine of x, would be our basic sine curve. I can write y equals the cosine of x minus pi over 2, and it would shift the entire cosine function, which would normally start here and go down and then go up again and then end here. Instead of starting here, it would start here. So like here, I meant to say, like a height of 1, it would start here, and so your cosine would actually line up perfectly with your sine function. So you wouldn't even be able to tell the difference between the two. And we can say if we had y equals cosine of x, we can rewrite the sine function. So again, y equals cosine of x, our basic cosine function, like that. If I wanted to rewrite it, I could write y equals the sine of x plus pi over 2. And instead of being my sine function that would start here, if it was plus pi over 2, it would start here, and we would get something that lines up perfectly with cosine. So you can phase shift one to turn into the other, and this is a great graph to be able to understand that. Okay, the way they characterize it, they're good friends. They follow each other exactly 90 degrees apart. Now, how can I find tangent values without a calculator? So I want you to take a big step backwards and go back and remember what we learned in geometry. In geometry about SOHCAHTOA, which is everyone's favorite mnemonic for remembering that the sine is the opposite over hypotenuse. So the sine of this angle is opposite over hypotenuse. Cosine is adjacent over hypotenuse, right here. And then tangent is opposite over adjacent, right here. So, again, just writing that out here, we have opposite over hypotenuse. And this one is adjacent over hypotenuse. And then I want you to notice that the hypotenuse values, if I then took and wrote sine over cosine, it would be the same thing as finding the ratio of these two values. Well, what would happen is the hypotenuse values would cancel, and we'd get opposite over adjacent, and guess what, guys? That's tangent. So the sine of theta over the cosine of theta is the same thing as the tangent of theta. And that is how you're going to find your tangent values without a calculator. Okay, so how can I do this with the unit circle? Well, let's look at finding the tangent of 0 degrees. Well, the tangent of 0 degrees is going to be equal to the sine of 0 degrees over the cosine of 0 degrees. So in this case, that's going to be 0 over 1, which is just 0. Let's find the tangent of 30 degrees, which is pi over 6. For those of you still working on your unit circle values. That means I want the sine of 30 degrees over the cosine of 30 degrees, which means that I'm going to be writing sine over cosine is, this first one is 1/2 over root 3 over 2. Well, the 2's are going to cancel, which means that gives me 1 over the square root of 3, which we learned has to be rationalized. That denominator has to be rationalized by multiplying by root 3 over root 3. So I'm going to get root 3 over 3, and that's the tangent of 30 degrees. And that's how you're going to find your tangent values. Okay, let's do one more. The tangent of 45 degrees. Well, the sine and the cosine are the same at that location. So sine over cosine, if they're both the same, then the tangent of 45 degrees, well, that's 1. And these are values I can use to help myself find what the graph of the tangent function looks like. Now, before we continue, what happens when I get, let's make it a different color. Let's make this one red, because this is like a Mayday moment. What if I find the tangent of 90 degrees? Well, that would be, again, sine over cosine, right? So that would be 1 over 0. Uh-oh, Mayday, Mayday, alert, alert. We can't have that. That can't be right at all. So the tangent at 90 degrees is undefined. In fact, as you get closer and closer and closer to 90 degrees, your tangent values just keep getting bigger because you're putting a bigger number on top of a smaller number, and that ratio is getting larger and larger. So what happens there is actually the tangent goes towards infinity, and we end up with our old friend asymptote. Okay, my y looks like a v. Asymptote. We end up with our old friend asymptote. Let's look at it. Okay. So, completely different shape from sine and cosine. Goes between negative and positive infinity. And what I'll have you notice is that at pi over 2, which is 90 degrees, we have an asymptote. And then again at every multiple of pi over 2 all the way throughout. So on tangent, the period of tangent of the basic tangent function is not 2 pi, it's pi. It starts, let me trace one of them. So here's negative pi over 2 function to positive pi over 2. And that is a distance of 1 pi in between. Okay, that is a distance of 1 pi in between. So with that in mind, you still have some of the same things that you had before with the other functions that we can use. You can still say y equals, well, let's go back and make it the right color. A times the tangent of bx plus c and plus d. So you can still have the same types of movement, but this time, what I want you to do when you're trying to figure stuff out here is to find the asymptotes. I want you to take bx plus c, I want you to make it equal to pi over 2. And whatever value of x you get for that, that is an asymptote. And every multiple of the period, or every distance of the period of the function away will also be an asymptote. So, how else can I use my other values, my other tangent values here? Well, if you recall, we had 0 degrees, we had a tangent of 0. Okay, so this is x's and then y's for the basic tangent function. This is y equals the tangent of x. When we had pi over 2, we had undefined. But in between, when we had pi over 6, you had root 3 over 3. Well, that's not very helpful. When you had pi over 4, oh, that one was easy. You had 1. Well, look at the halfway points here between pi over 0 and pi over 2. If you look, there's the dot right there. Let me make an actual dot. Right there. And you can see that at negative pi over 4, where one of the two values, in this case the sine value is negative, you get a -1 ratio of sine to cosine. And look, at negative pi over 4, there's -1. So once I have those, and then this center value here, which is halfway between the asymptotes, if you look, halfway between these two asymptotes, once I have that and those, I can draw that lovely curve. All right, and tangent has different things that we can say about it. Usually you end up graphing 2 periods of tangent, so in this case I would probably graph both of these. And you also want to make sure that you have those asymptotes clearly marked here and here and here. Whoop, I missed for that one. Sorry about that. All right, guys, happy graphing of the tangent function. I will see you in class.